In this circuit, we're looking at basically a series circuit with some parallel elements thrown in. And we're also using a current source this time instead of our voltage source. So let's take a look at this circuit and do some analysis with it. I think what's best to do here is I'm going to look at each of these impedances as block impedances. So for instance, R1, I'm just going to call that Z1. For this block here that has an inductor and capacitor, I'm going to call that Z2. And for my block impedance here, I'm just going to call that Z3. You could call it ZA, B, C, or whatever. But let's do this. And so what I'm trying to have happen is that I'll just have these three block impedances all in series. And once I find those, I can just add the impedances and then work through this as if it were a series circuit. Z1, Z2, Z3. All right, so let's find our block impedances. Z1's pretty easy. It's just ZR. So the impedance of our resistor, of course, is 2 at 0 degrees, or 2 plus 0J. So I can just write that as 2 and leave it at that. Z2 is actually going to be our capacitor impedance in parallel with our inductor impedance for the inductor L1. So I'm going to use my product over the sums. So we've got a negative 4J times 6J over negative 4J plus 6J so that should give me about negative 12.5J, or 12.5 times to the negative 90, or negative 12.5J, whichever form you want that in. Z3, now for the three branches, I cannot do the product over the sums. So in that case, since I'm going to have ZR2, ZR3 in parallel with ZL2, I'm just going to do it like this. 1 over 8 for R2, 1 over 8 for R3, 1 over 3J for L2. Now I could have combined the 8 ohm resistors and then I could do product over the sums with the 4 ohm resistor that would result from that. But I'm going to do it this way instead. So what we should have there in polar form is 2.42 at 52.85 degrees. Let me work that out for you in rectangular form in case that's what you're working yourself here. Okay, so in rectangular form, that should be 1.46 plus 1.93 times J. Okay, so whichever version you use is fine. Now, when we're looking for our total impedance, that's going to be our Z1 plus Z2 plus Z3. So you can add those in rectangular form. Z1 was 2. Z2 was minus 12.5J. And Z3 was 1.46 plus 1.93 times J. So the total there should be about 3.46. So we would just add the real parts and then add the imaginary parts. So minus 10.57J, or in polar form, if you're working through it that way, 11.12 at negative 71.87 degrees. Okay, so either of those is fine. All right, so what else are we looking for here? We want to find V2. And V2 is where in our drawing? V2 is here, okay? So that's the voltage drop across Z3. So to find V of Z3, which is V2, that's what we're looking for, we could take our source current and multiply by Z3. We could also do the voltage divider rule if you wanted to do it that way. It would just be Z3 over ZT times, actually we don't have our total voltage, do we? We'd have to find that first. So let's continue this way. So we've got our source current, which we were given, that's our source that's our source for the circuits. We were given 5 at 0 degrees, and Z3 was 2.42 at 52.85 degrees. So there we have about 12 volts, 12.1 at the 52.85 degrees. What else are we looking for here? We're looking for IL, which is the current through our inductor. So we're going to use the current divider rule here. Now, if you had two branches, you could take that shortcut equation that we were using in DC. However, since we have three branches here, I'm going to use the standard form of the current divider rule, where you would take the total impedance divided by the impedance of the branch where you're looking for the current times the total current through the circuit. Okay, so ZT, and for ZT, I'm actually talking about Z3, not the total impedance of the entire circuit. This is the total impedance of the divider, okay? And this right here is the divider that we're looking at, because that's what's going to divide our source current, okay? So it's actually Z3 over ZL times the total current coming in. So we've got ZT here. Um, 2.42, 52.85 degrees over ZL, which is 3 at 90 degrees, times IT. Again, that's just the 5 amps of current there. So the nice thing about polar form for multiplication and division is you can just focus on the magnitude first. So 2.42 times 5 divided by 3 gives you about 4 amps here. And then your angle would be the angle in the numerator added to the angle for the current, which is 0, and then subtract the angle in the denominator, which is 90. So that's about a negative 37 degrees there. Now, if you wanted to check that current, remember V2 that we just found, that's actually the voltage drop across that inductor. So IL should also be V2 over ZL. So if we had 12.10 at 52 degrees, oh, that's 3, not 2, at 3 at 90 degrees, we should get about the same thing. So we should get right about 4 and negative 37.15 degrees. Okay, so feel free to work out the rest if you want to. If you find the current through R2 and R3, for instance, keep in mind that IR2 plus IR3 plus IL2, which we just found here, should equal that source current, which is 5, right? So feel free to work through any of these, because you can check your own answers at this point, because you know that the currents would have to add up. So the current through the capacitor here and the current through this inductor would have to add up to 5 as well. If you found your voltage drop here, here, and we already know this voltage drop, those should add up to the total. We didn't find the total voltage drop, but VT would just be ZT times your source current. So you can always check your own answers, but with AC you're going to want to use the calculator to do that. It's just a little harder to see it intuitively, because the numbers don't really seem to add up until you actually plug them into the calculator.